Polyprotic acids. Polyprotic acids are characterized by having more than one acidic proton. Here are some examples: sulfuric acid, phosphoric acid, carbonic acid, oxalic acid. In every case, you can see that there's more than one acidic proton. Polyprotic acids have a Ka value for each proton that can be removed. For example, consider carbonic acid, H2CO3. The first ionization equation for carbonic acid is H2CO3 in water produces HCO3- and H3O+. Write the Ka expression for this equation. Since this is the first ionization reaction, the first proton removed, it is referred to as Ka1. And it's the same as any other equilibrium expression. The ratio of the concentration of the products, HCO3- times H3O+ concentrations, divided by the reactant or the acid H2CO3. A second proton is removed, leading to the second ionization equation for carbonic acid, where we start with HCO3- in water to produce carbonate, CO3 and the hydronium ion. Write the Ka expression for the second ionization reaction. This is referred to as Ka2. It's the concentration of the products, CO3 times H3O+, over the concentration of the reactant, HCO3-. The bicarbonate ion, HCO3-, appears in each expression, circled in red, in the numerator for Ka1 and in the denominator for Ka2. The product of Ka1 and Ka2 for a diprotic acid yields the overall Ka for the complete dissociation. So if I multiply these two Ka values together, here's the first multiplied by the second, we see that that bicarbonate appears in both the numerator and denominator, and this simplifies to CO3 concentration times H3O+ concentration squared over the concentration of H2CO3. The equation for the complete ionization of carbonic acid is H2CO3 in water produces carbonate ion and 2 hydronium ions. And the Ka expression for the reaction is concentration of CO3 times concentration of H3O+. This coefficient gives us a square here over the concentration of the H2CO3. There is usually a large difference with the ease in which these acids lose the first and second protons. Sulfuric acid, for example, is a stronger acid because Ka1 for the loss of the first proton is 1.3 times 10 to the third, much larger than 1. In a 1 molar aqueous solution, all the H2SO4 molecules lose the first proton to form HSO4-, shown by the dissociation here. And that Ka1 value is very large at 1.0 times 10 to the third. The Ka2 for the loss of the second proton is only 1.2 times 10 to the -2, much, much smaller, which means only about 10% of the H2SO4 molecules in a 1 molar solution will lose a second proton. So this dissociation of the second proton is much less likely to happen due to this small Ka value. If the difference between the Ka1 and Ka2 values is 10 to the third or greater, you can assume that most of the protons are available at the first stage of dissociation. The Ka1 value can be used by itself for any subsequent calculations.